Welcome everyone for this afternoon session at PLDI dedicated to probabilistic analysis. We will have 6 exciting talks, and the first of them is from John Lee from Northeastern University. He will be talking about Lilac, a model separation logic for conditional probability.
Okay, hello everyone. I'm John, and I'll be talking about this modal separation logic I've been working on called Lilac. It's joint work with Amal, Ahmed, and Steve Holtzen at Northeastern University. Okay, so the goal of Lilac is to try and be a program logic that can reason about complex probabilistic systems. As everyone here is probably already aware, machine learning components are being used increasingly in software systems that do important things, like drive cars, make decisions, or do science. And in each of these cases, we want guarantees about the behavior of those systems. Cars should be safe, decisions should be fair, and scientific results should be significant. Now, usually these systems are very large and composed of multiple interacting components, each probably probabilistic in their own ways. And so it should be possible to take components that you've verified in one way or another and link them together into a verified component for a whole system. So this is kind of the goal of Lilac, is to serve as a logic in which this kind of modular reasoning can take place. And the idea is that we can exploit this phenomenon that occurs in probabilistic programs all the time, which is probabilistic independence. So probabilistic independence is this thing that arises frequently and naturally in probabilistic programs. And to convince you of this, I'm going to present 2 examples. So first, suppose you're making like a neural network and you randomly initialize the weights of your model. Well, naturally what you're going to get is an array whose elements are independent random variables, right? As another example, if maybe you're a scientist and you've collected a bunch of observations about the world and you want to get maybe a more accurate estimate of whatever you're measuring, you may take an average of those observations, and of course there are these standard theorems in probability theory that say, yeah, you can do that. You can average a bunch of data points and you get a more accurate estimate, assuming that your data points are independent, right? So all over probability there are these things where maybe you have a procedure, it takes independent inputs, or you have a function, it produces independent outputs, and there are all these kinds of side conditions to do with independence. And so you're kind of naturally led to the idea of maybe we can use a logic that naturally captures the notion of independence in a modular way. So that's the idea of Lilac. Use separation logic to do this. Quick review of separation logic. Separation logic is this tool used for reasoning about heap-based programs. So here I have a heap-based program. It allocates 2 mutable references, one containing a 0, one containing a 1. And at termination, separation logic allows you to conclude that x points to 0, y points to 1, and then that x and y point to disjoint heap locations. That's expressed by this special separating conjunction star. The power of separation logic comes from a particular inference rule that it has called the frame rule, which says that if I want to reason about a particular program E, I can ignore all of the parts of the spec that are talking about heaps irrelevant to whatever parts of the heap the program is manipulating, called the frame. And this particular rule basically lets you focus in on only the parts of the heap that your program is concerned with. Indeed, this kind of modular reasoning principle and the notion of separation in general has led to the creation of tools that can reason about large software systems that use heaps. And so the hope is that in Lilac we can do the same thing, but for probability. And so we have a separation logic where every time you write separating conjunction, instead of meaning something about disjointness of heaps, it means something about independence. For example, I've replaced that imperative program on the previous slide with a program that just flips 2 coins, so that generates 2 random Boolean values. And in Lilac, we can conclude that after this program terminates, you get 2 random variables that are Bernoulli distributed with parameter 1/2. And we can use this separating conjunction to state the independence of those random variables. Now, this is not a new idea. People have noticed that separation and independence are kind of similar. And some of you may be aware that there are papers about this. There's this paper that introduces a logic called PSL, in which there's this notion of separation, and the separation enforces some kind of independence. And also this idea has been developed further to export more exotic forms of independence. So you may be wondering, what's new in Lilac? What do we build on this? And I want to convince you that there are actually a lot of things that are new in Lilac. First of all, Lilac has a simple frame rule. So I mentioned on the previous slide that separation logic has this frame rule, and it's like fundamental to the modularity of reasoning principle. In Lilac, the frame rule looks identical to the frame rule of ordinary separation logic. And this has many benefits. It means that checking whether or not you can reason locally about your program works exactly like when you're reasoning about an imperative program. So the same kind of intuitions that you have about framing, they apply directly to the probabilistic setting. Also new in Lilac is a richer notion of independence. So I want to go back to this neural network example I had on the previous slide. I said that the elements of that array are supposed to be mutually independent. And indeed, in Lilac, you can state this mutual independence using an iterated separating conjunction. So each conjunct here is talking about a single array element, which means the iterated separating conjunction says the elements of the array are independent. Now, this kind of independence relationship is not expressible in PSL and the derivatives that I was mentioning earlier, which makes Lilac have a richer notion of separation. There are certain kinds of independence relationships that it can capture that previous work could not. In fact, we also prove that it captures all independence relationships. So we have a theorem that says whatever two random variables you might have, if they're independent, that is semantically modeled by a separating conjunction. Also new in Lilac is the ability to support quantitative reasoning about programs. So earlier I had this example about a scientist wants to aggregate some information that they've collected from the real world. And this statement about how doing this is okay is expressed in the language of probability theory using quantitative operators like expectations and variances, right? So you might say that, well, if the elements of the array are independent and they have the same expectation and some bounded variance, then when I take their average, I get something that still has the same expectation but a smaller variance. In Lilac, we can express these kinds of things. We have connectives for talking about expectations of random variables and variances, and for talking about inequalities on real numbers. And also, for this independence constraint, we have the ability to express mutual independence of the elements of the array using an iterated separating conjunction. The final thing that's new in Lilac, which I admit is a little bit subjective, is that we have this semantic model that we believe has better interoperability with ordinary textbook mathematics. So our semantic model is based on ordinary constructs of probability theory, and the upshot of this is that whenever you see something in a Lilac proposition that looks like pen and paper probability theory, it basically is pen and paper probability theory. For example, this variable here, that's just an ordinary random variable. This expectation and variance, those are mathematical expectation and variance, and so on. And the advantage of this is whatever manipulations you might want to be doing in your proofs that you already know from pen and paper, they carry over directly to formal proofs in Lilac. Okay, so all of these benefits that I've just described basically follow from one single idea, and that's kind of the key idea of this paper. So I'm going to get into some of the technical content of what that is. And that idea is that probability spaces, these objects from probability theory, are the heaps of probability. So what does that mean? Well, to explain that, I want to break down this statement here, that X is Bernoulli distributed with parameter 1/2. So this, let's just think of this statement as an ordinary pen and paper math statement, not like a statement in any formal logic. Now, working informally, it looks like it's pretty simple, right? It just says, okay, well, X has probability 1/2 of being true, probability 1/2 of being false. But really, there's a lot that this notation hides. There's a lot of machinery that's happening under the hood to make probability theory go. And if you kind of peek under the hood, you'll find that there are a lot of interesting objects. There's a sample space, omega, right, which models like this set of possible probabilistic worlds you could be in. And X is not a Boolean value. It's not either true or false, right? It's a function out of this sample space that's true in some possible worlds and false in some possible worlds. These sets of possible worlds are called events, right? And they're given probabilities by a probability measure. And the interesting thing about probability theory is that not all of the subsets of omega are necessarily events. So when you say that X is Bernoulli distributed, you're actually saying a lot of stuff. You're saying that this blue thing and this orange thing, those both have to be events. And then when you plug them into your probability measure, you get the right probabilities out. So there's a lot of stuff here that's happening that you usually never want to see when you're working in probability theory. Right, you have this sample space, you have what qualifies as an event, you have the probability measure, and the whole idea of probability theory is that it's designed to abstract over all of these objects. You don't really want to talk about them explicitly, you only want to access them through the nice interface that probability theory provides using constructs like random variables, the probability operator, the expectation operator, and so on. Now, as you might have guessed, if you put these three components together, you get what's called a probability space in probability theory. And so there's this interesting situation here where you have this nebulous object. It's kind of messy. You don't want to think about it. and you access it abstractly through a handle, a random variable. And that kind of looks like the situation with imperative programming, right? We have this weird object. It's a big heap. I don't really want to think about the details of it. And I can only really touch it indirectly through these references, or through these locations into the heap. And it turns out that this correspondence kind of just, it works all the way. So you can actually even think of a probabilistic program as carrying along an extra probability space and just like changing and altering it, just like an imperative program carries along a heap and changes and alters it. So just to explain this, let's go back to that imperative program from the previous slide. So we all know how this works. You run new0, you get back a heap chunk with 0 in it. You run new1, you get back a heap chunk with 1 in it. And now because of how allocation works, every time you allocate something, you get a fresh thing. The heap at the end is going to be a disjoint union of the blue heap and the red heap. Now it turns out you can do the same thing for probability, right? So I have this two-flip program. The first flip I can think of as generating a fresh random variable that's backed by some fresh probability space. And same for the second flip. I can think of it as generating a fresh random variable backed by a red probability space. Now, just as at the end of that imperative program, the final heap was a disjoint union of a blue heap and a red heap, at the end of this probabilistic program, the final probability space is going to be some probability space disjoint union of a blue probability space and a red probability space. This disjoint union operator is an operator that we've constructed called an independent combination of probability spaces. And it basically is like disjoint union, but for spaces. So it's a partial function on probability spaces, and it satisfies all the algebraic properties that you might expect. Also, as you might expect, this independent combination then becomes the interpretation of separating conjunction. Right, so in ordinary separation logic, a heap satisfies a separating conjunction if you can split it into two parts that individually satisfy the conjuncts. Well, in Lilac, it's exactly the same. It's just that we replace the heaps with probability spaces, and then we replace the disjoint union with separating conjunction. And now from this, we kind of get all the nice things that I was talking about before. So because we chose the interpretation of separating conjunction to be like this, we kind of are forced to have a frame rule that just works exactly like the normal frame rule. And because independence is operating on probability spaces and really can only mean probabilistic independence, we get that every independence relationship is validated by our model. And because we're working with probability spaces, these standard objects of probability theory, it kind of forces the rest of the model to also work with standard objects of probability theory. And so we get that good interoperability with ordinary math that I was talking about before. So kind of this is like the main result that we have in our paper, is that like from this insight we can get like a really nice separation logic, and it all kind of flows from this one thing. But there is another thing that we did, which is why the paper title is a modal separation logic for conditional probability, and not just a separation logic for probability. And that's that we have a modal approach to reasoning about conditioning. So conditioning is this tool that you can use in probability theory proofs, and often it can drastically simplify your proof or let you do cases on a particular random variable. And we model this phenomenon in Lilac with a modality. Concretely, it looks like a proposition of this form, which says that the proposition P holds conditional on the event that you fix some random variable big X to a particular value little x. And the nice thing about this modality is that if you stick it in front of other propositions, everything just gets like the intuitive conditional reading that you would expect. So for example, we've seen that this proposition asserts that x and y are independent and that they're both distributed as Bernoulli 1/2. Now when you put the conditioning modality on front of it, this star now asserts conditional independence, and x and y are now conditional distribution Bernoulli 1/2. And same thing happens with other propositions. So we have propositions for expressing probabilities and expectations, and when you stick conditioning in front of it, it gives you propositions about conditional probability and conditional expectation. And then we prove a bunch of laws which express intuitive facts about the conditioning modality and also let you import some standard theorems of probability theory. So just to whet your appetite for this, I'm going to put up this rule on the slide. I'm not going to explain it, but I'm going to claim that it's the law of total expectation. And if you're interested, you can check out the paper and see how that works. So I'm running out of time here. So we use Lilac to verify a lot of examples from prior work, and also a tricky little weighted sampling example that kind of exercises all of the features that I just talked about so far. So it uses continuous random variables. It has this correctness specification that involves needing to compute an expectation. It needs to maintain this loop invariant that says like there's this independent structure that's built up at every loop iteration. And finally, to complete the calculation, you need to condition on just the right thing, and we use the conditioning modality to get that to work. Also in the paper, you'll find like the semantics of the conditioning modality, where we import some interesting theorems from probability theory. you'll find this insight, which I didn't really get to talk about, which is that there's a fun little correspondence between the notion of ownership from traditional separation logic and the idea of measurability of a function from measure theory. You'll find lots of detailed worked examples, and you'll also find another thing I didn't get to talk about, which is the ability to say that two random variables are equivalent. And if you're a separation logic person, this proposition is duplicable, but it talks about resources in a certain way, so that might be interesting to you. If you're interested in any of this, please check out the paper. The full version of the paper is in the bottom left corner over there. If you have any questions, you can, of course, email me or any of my co-authors, and I'll just leave you with this picture of the correspondence that this paper is based on. Thanks.
Questions?
Hi. So since Lilac itself can be seen as another way to abstract probability theory, do you think that this has applications outside of computer search programming, especially in in a standard mathematical environment?
Possibly. That would be really cool. Personally, Lilac kind of grew out a project to understand probability theory myself, and I do think it makes certain concepts more intuitive to me as someone who came from more of a separation logic background. I know there's also some relationship to the synthetic probability and synthetic measure theory stuff that people are interested in, which is kind of like a way of like reimagining probability theory. So that would be interesting as well. Yeah.
All right, thank you.
Hello, so I actually have two questions first. So you mentioned that you're modeling those conditional probability as modality, but like before I listened to the talk and just read the description, I thought, wait, is a conditional probability going to be like separating implication? And so I thought, does that not work for some reasons, or is that like an alternate approach, or have you looked into that?
Sorry, I couldn't make out the question fully, so it was like the conditioning modality enables simplification.
So like there's, in separation logic, there's, aside from separating conjunction, there's also a separating implication operator that's kind of supposed to be like implication by separating.
Oh.
And so I was wondering if you like tried to use that and had some trouble with that, or?
Yes, the separating conjunction is, the separating implication is super interesting. It becomes kind of the interpretation of sampling. So when I sample a new thing, I want to kind of conjoin this independent probability space onto my current probability space, and you can express that with this separating implication.
Ah, I see. So it's actually a different thing. Okay.
Oh, okay. Sorry. Maybe we can talk after.
Okay. Actually, also a second question. So here, so now we have a separation logic for mutable state, and we also have a separation logic for probabilistic non-determinism. And so one thing one can notice here is that both of those things can be expressed as a monad. And so I wonder if you, like maybe if there's some existing work about that correspondence, if there's some like generalization of both of mutable state and non-determinism that like makes separation logic possible, or have you not looked into that?
Yeah, I think there probably is, but I just don't know it. I do know that, like, probability, there's some result that it's some kind of affine commutative monad, so you can like reorder things, and you can discard things without worrying about leaking memory, because that's not really a thing. But I don't know the details. Yeah.
Okay, thank you.
Yeah.
Any more questions? Then let's thank the speaker, and then.